Okay, welcome back everyone after Thanksgiving break, and today we have Jennifer Whyte from the University of Pittsburgh. Jennifer and I did overlapped at our PhDs at the History and Philosophy of Science program at Pittsburgh, so it's a real pleasure to see her back. Today she's going to tell us about search for extraterrestrial intelligence and mathematics and open texture and everything else. So take it away, Jennifer.
All right. Well, thank you all for showing up on this chilly December morning. It's a pleasure to be here. So there are multiple kinds of projects, right? They're the projects that you come to after, years of deep research on this one specific topic, refining the question down until you've got something perfect. And then there are the projects that come to you when you're reading two different literatures at the same time and notice a funny coincidence. This is one of those talks. So today, we are going to talk about aliens. And despite the science fiction topic, we are going to take this seriously. The topic of extraterrestrial life is a deep well for philosophical reflection, particularly on topics like concepts, language, and communication, which is why these topics are such rich fodder for the more philosophical kinds of science fiction. Like this one, and this one, and this one, and even this one, arguably. But in all of these films, the topic of how we come to understand the alien other is one that we answer when the other is standing right in front of us. When we have indeed made contact, not merely by our communications devices, but physically. That's not actually the situation we have to contemplate when we talk about alien communication in a more realistic way. If they're out there, they're certainly not around here. The basic question of this talk is, how much similarity must we presume that we have with these hypothetical alien interlocutors in order to be confident that they will be able to understand the messages that we send to them? And the answer I'm going to come to is that even an arbitrarily high degree of similarity between ourselves and the aliens is not sufficient. Now, that might seem like a slightly obvious wet blanket type question and answer. So I'll let you in on the secret bonus question. The real question is there any concrete circumstance in which the answer to the question, are mathematical concepts open textured in the Weissmannian sense, where that question makes a difference? I'll talk about what that all means in a second. Basically, this is a philosophy of mathematics question. Philosophy of mathematics is typically quite an abstract domain, one that has very little to say about the world, and that the world has very little to say about. I'm going to argue that this is a context in which a philosophy of mathematics question makes a concrete difference in the world, and one we might even be able to tell someday. We don't want to be chasing squirrels around trees here, right? The spirit of pragmatism compels us to look for why things matter. All right, so this is what I'm going to talk about in brief. First, I'm going to talk a little bit about the technical and engineering limitations on how we send messages to aliens in the hopes of being understood by them. Then I'm going to mount a kind of mock dialogue, arguments both against and for the feasibility of these strategies, coming first from late Wittgensteinian philosophy of mathematics, and then later from a new argument that I'm going to propose, drawing on the work of Friedrich Waismann. And then I'm going to show that this argument has more teeth than the Wittgensteinian. So let's set aside for a second the question of whether there are any aliens to contact, or whether or not it's wise to contact them. Those are both interesting questions, of course, but for our purposes, they're actually moot points. We have tried to contact aliens already several times. Most familiar are the golden records. And of course, they're very, very cool and very carefully thought through. But you are all physicsy enough people to know that, that these are very unlikely to work. There's just not that much you can do with a bit of metal flying through space. It's not a good way to communicate when you don't know where your interlocutor is, and it's not a good way to do it quickly. The better way to do it is with radio. Why radio? Two reasons. First, electromagnetic signals travel fast and coherently through space. Radio signals are particularly stable. And more importantly, you can probably persuade your government to build you a radio telescope, which you can then use for other things, rather than an apparatus that you can use only to try to send messages to aliens. And of course, we sent a bunch of messages through these means as well. These include both publicity stunts. NASA sent some Beatles music into space. A Doritos commercial as well. Now, aside from the fact that we have no reason to think that the aliens will particularly enjoy either the Beatles or Doritos, thankfully, these are doomed to fail. Neither of these messages were sent with any particular attention paid to the coherence of the signal as it travels through space, nor its receivability. So we don't have to worry that they're going to show up and ask where the cool ranch is. But there are also serious efforts. Transmission of radio signals that have been specifically designed to be interpreted by a hypothetical other. And those are what we're going to talk about today. First, a quick terminological aside. You probably know this already, but pays to be clear. There are a couple of different names given to the practice of sending messages into space for the hypothetical interpretation of aliens. Most common is active SETI, where SETI is Search for Extra-Terrestrial Intelligence. Sometimes you see SETI with a C. That was an older term. It's now mostly out of use because it's also, the acronym SETI is also used for attempts to communicate with whales. And then there's METI, Messaging Extraterrestrial Intelligence. That's explicitly an active program. There are subtle distinctions in meaning between these three that I can get into further. But for now, I'm going to say that I'll stick to the term METI for the rest of this talk because it unambiguously refers to message sending. So, how do we send a radio message to space? Radio signals can travel a very long distance, and they're relatively stable. They're definitely a good choice here. But we clearly can't just beam the aliens the CBC and expect them to be able to pick it up. The most obvious problem is the lack of a shared language, but the more fundamental problem is the lack of a shared radio protocol. The aliens simply don't have the transducer in your radio that converts the modulated radio wave you receive to the soothing voice of Peter Mansbridge. Now, this is hardly a novel observation. Aliens don't frequent Radio Shack. And the first serious effort to make a workable METI project took that into account. Here's how that worked. The strategy is to build a message that can decode itself without the need of a transducer in the radio. The strategy here was pioneered by Frank Drake, that's him, and so it's often referred to as the Drake Pictures strategy. The first message sent using the Drake Pictures strategy gets called the Arecibo message. Now, the Arecibo message is a series of 1,679 binary characters, that is, one low and one high frequency oscillating back and forth 1,679 times, transmitted on these two alternating frequencies. The idea is that an intelligent alien receiver of the signal would notice that the coherence of the signal and the two frequencies, and know that the signal consists of these 1,679 characters. Now, the binary string has no obvious meaning on its own. However, if the alien knows their number theory, they may notice something interesting about the number 1,679. I have repeated it very often so that you might notice it as well. It's not an ordinary number. It's a semiprime, the unique product of the prime numbers 23 and 73. if the message, all 1,679 characters, is arranged one after the other into 23 rows of 73 characters in the order in which they were received, the message forms this image. Well, that doesn't look quite right, does it? But it doesn't look totally random either, right? I've read my Dennett. I know a pattern when I see one. Presumably the aliens have too. So let's try the other way around. That's a bit better. Now, this is clearly a message with some information in it. As you can see, there's even a little guy. When the sections are colored in, they look a bit like this, and it becomes a bit more comprehensible. Up at the top there, you've got representations of numbers from 0 to 9. The green bits are representations of the nucleotides in human DNA, with each of the columns representing the elemental number of one of the elemental constituents of the nucleotide. You've got the double helix structure of DNA. Then you've got our little fella, the location of the Earth relative to the sun, and then an image of the Arecibo telescope itself. A lot of focus on DNA for some reason. We'll get back to that. Now, maybe you're not convinced that this particular message would be particularly intelligible to our alien interlocutors. Arguably, it's not particularly intelligible to humans either. And in truth, this is an intentionally simple proof of concept. The more serious attempts do work on the same principle, though. Send the signal as a string, assume that the aliens can put it into a grid, and make an image that way. Prime factors become axes, become images. The question on our plate is now, is this going to work? Is this a good strategy? So the NAIC certainly thought so, and they argued for it in a paper published collectively in 1975. They say that the fact that 73 and 23 are prime numbers facilitates the discovery by any recipient that the above format, of the previous slide, is the correct way to interpret the message. So there are two claims here that they think we can get out of these messages. First, prime factorization is presumably sufficiently universal that our alien interlocutors will definitely know what to do when they see a semi-prime number. And also, anyone who has discovered this, has decomposed the message in this manner, will know with absolute certainty that they have done it correctly. The first point is the one we're interested in here. So let's get into that. So, I wouldn't be a philosopher if I never said this. The most obvious philosophical point to make when faced with an argument like that everyone knows what prime factorization is the Wittgensteinian rejoinder. If a lion could talk, we would not understand him. Maybe suitably modified. Philosophers, after all, are no strangers to the question of the feasibility of alien communication. We've been doing it at least since Euler proposed to build a Pythagorean triangle visible from space in Siberia, and Kant started musing about the starry sky above him. But Wittgenstein here is probably a more useful jumping off point. This is a very famous remark. There's a lot you can say about it. There's a lot that people have said about it. But the basic idea is that even if the boundary of language that separates us from the lion or the alien could be transcendent, the lion's form of life is so different from our own that it would give rise to a kind of speech that is incomprehensible to us. The lion lives in such a way that we cannot assume that the lion shares any concepts with us, or even conceptual roles. When humans who don't share a language come to understand each other, as has happened many times throughout human history, it's based on the fundamental similarity of human forms of life. We're just not that different from each other. That's not quite true of a lion. And of course, we're not even proposing to talk to lions. Lions are mammals. They share a common ancestor with us a mere 95 million years ago. setting aside any thoughts about panspermia, we share no evolutionary history whatsoever with our putative alien interlocutors. We can't presume to have any similarity in forms of life with them at all. Now, I sense that an objection might be coming. Here's an objection. Wittgenstein's argument is about language, but I haven't said anything about language so far. I've been talking about mathematics. We're not proposing to use language to talk to the aliens. That would be an obvious non-starter. This is Francis Crick, quoted in a volume compiled by Carl Sagan in 1973, which summarizes the proceedings of the first International Communication with Extra-Terrestrial Intelligence conference. It's a fascinating volume. All kinds of characters you wouldn't expect show up, including Francis Crick here. And he basically makes this argument that I think it probably occurred to many of you. Mathematics isn't language. It's something more like a natural language. We can assume that it's going to be common to both us and them. It's also easily put into a form that's easily transmitted, like we're doing with these binary characters. And there's some intuitive plausibility to this, right? The Pythagorean theorem isn't false on Mars. Mathematics is, putatively, universal. An alien might not agree that the sky is blue or snow is white, but they will agree that 1 and 1 is 2. As a point of commonality that we can use to ground our communications. At that first International SETI conference in 1971, this point was made explicitly by Crick here. By the way, you were wondering why there's so much DNA in the Arecibo message? There's your answer. But this is not an uncommon refrain in the METI world in general. Crick even claims in this volume, in response to a somewhat skeptical remark by the historian William McNeill, that any mathematician would argue that math has this universal character. But there's a way we can push back on this from a Wittgensteinian perspective as well. This is a longish quote, so I'm not going to read all of it. We can come back to it later if you would like to read all of it. This is a short paper by Bronwyn de Bruin, or Boudewijn de Bruin, sorry. That is sort of narrowly targeted to the point that the late Wittgenstein has the resources to push back on Crick's claim that mathematics is a universal natural language. For one, mathematics isn't a language for Wittgenstein, but more importantly, the mathematics we have is not exhaustive of the mathematics that is out there. We develop the mathematics we use in response to our needs, in response to what we are trying to achieve. A world in which we try to achieve different things would have different mathematics without any of it proving any of it false. De Bruin is talking about Linkos, which is a different thing, not Arecibo, but the point works here too. Regardless of whether the truth of mathematics is universal or not, the actual mathematics that our world has is a consequence of the contingent history of our world. Maybe a different species' math would be totally different. Maybe they would have nothing in common with us mathematically. After all, we don't know anything about them, right? Do you sense another objection coming? Because I do. Is it actually true that we don't know anything about our hypothetical alien interlocutors? How sure are we of that? So this is Lev Gindelis, who was also at that conference in 1971, where he made this remark. It's not true that we don't know anything about our alien interlocutors, because necessarily, if we make contact with aliens, we know exactly one thing about them. A solution to this problem is facilitated by the fact that there are certain common elements designed neither by the sender nor recipient. Such an element is the communication link itself. By this link, I mean the region of cosmic space between the sender and the recipient, between their antennas, the interstellar and interplanetary medium, and their planetary atmospheres. We know one thing for sure about any alien who receives this radio signal, which is that they have a radio telescope. It's quite hard to receive radio signals without one. If they have a radio telescope, they must actually share quite a lot of scientific knowledge with us, even if it's not in a form that we would immediately recognize. They have to know how to build a telescope. They have to know how to factor out the interference of their atmosphere, or to build it in space where that is not a concern. They have to know how to correct for red and blue shift. They have to know quite a lot about the same sort of stuff that we know about that allows us to send radio signals. And Gindlis argues that, well, this actually guarantees that they're more similar to us than we might otherwise think. It's a sort of transcendental argument, right? The necessary conditions for the possibility of alien communication. And that's kind of a hopeful note, right? If that's true, then the method of Drake pictures doesn't fall apart for Wittgensteinian reasons, given what has to be true of any civilization capable of hearing our cosmic call. We probably added a factor of 10 to the negative 1 or 2 to the Drake equation that way, if we rule out all species that don't do that. But it's a big universe. The radio telescope argument guarantees that our alien interlocutors will have whatever mathematical concepts are necessary to build a radio telescope. That's a lot to work with. And indeed, contemporary SETI researchers, such as Jill Tatar, have taken "can build a radio telescope" on board as SETI's operational definition of alien intelligence, since there's just no hope of contacting anyone else. So Drake pictures like the Arecibo message weren't yet on the table when Gindlis made that argument, that dialogue was just about methods of communication in general. But the application is obvious, right? Does that shared scientific core necessary to build a radio telescope include the concept of prime number? Well, that's hard to say, but it's not implausible. And the Drake picture messaging technique was designed with this in mind. The only mathematical concept that our hypothetical interplanetary pen pals need share with us to read our message once they have received it is prime number. In the history of human mathematics, the concept of prime number is a fairly early development, right? It's old enough that we don't really know how we got it. It's a fairly basic bit of arithmetic in general, and it seems pretty unlikely that civilization could build a radio telescope without arithmetic. Now, I'm going to argue that even this similarity isn't enough of a guarantee for the success of the Arecibo message. The reason for this is that even if the aliens share a concept of prime number, there is no guarantee that they have our concept of prime number. This is because, I claim, the concept of prime number has exhibited a property called open texture in its history. I'm going to argue that this argument is more cutting than the Wittgensteinian ones we talked about before, because it still goes through if the aliens on the other end of our communication link are arbitrarily similar to us, whereas the Wittgensteinian argument was based on them being different. Let's get to it. So the concept of open texture is due to a guy called Friedrich Weissmann. Weissmann was a member of the Vienna Circle, at times collaborator with Wittgenstein. But the notion of open texture comes up more prominently in Weissmann's later work after he stopped working with Wittgenstein. Here's a kind of rough and ready definition of it. A concept exhibits open texture if, for some possible domain of the concept's application, nothing in the content or history of the concept is sufficient to determine if the concept applies to that domain. That is, open texture is a kind of insufficient descriptive capture of a concept. A perfect concept will completely separate the world into things that belong to the concept and things that don't. A concept with open texture fails to do that. And note that this is crucially a different concept than a different idea than a vague concept. A vague concept is one that fails to divide up the world neatly, and we know that, and it's okay. For instance, the concept pink does not completely sort the world into pink and non-pink things, because there's lots of areas between, say, pink and orange, where reasonable users of the language can say either that's pink or that's not pink without really disagreeing with each other. In the case of open texture, that's not true. The concept is supposed to be precise, but it isn't. Here's the classic Weissman quote where he lays out this idea. He says, "Suppose I have to verify a statement such as, there is a cat next door. Suppose I go over to the next room, open the door, look into it, and actually see a cat. Is this enough to prove my statement? Or must I, in addition to it, touch the cat, pat him, and induce him to purr? And supposing that I had done all these things, can I then be absolutely certain that my statement was true?" Instantly, we come across the well-known battery of skeptical arguments mustered since ancient times. What, for instance, should I say when the creature later on grows to a gigantic size? Or if it showed some queer behavior usually not to be found with cats, say if, under certain conditions, it could be revived from death, whereas normal cats could not. Shall I, in such a case, say that a new species has come into being, or that it was a cat with extraordinary properties? The idea here is not that we are making a mistake by using the concept of cat in the ordinary way we do. It's not even that the concept of cat is vague. In all situations we are likely to actually encounter, cat is perfectly precise and our application of it is seamless. But lurking around the edges of conceivability are possible cases in which the putative cat could exhibit properties that would throw us into confusion about how to use our language. Is this a weird cat or not a cat at all? And most importantly, if you found yourself in this situation, forced to answer the question, is this or is this not a cat? You would have no conceptual or logical resources to which to appeal. There's nothing in the concept of cat that will settle this question for you. The concept of cat is just silent on the question of spontaneously growing and shrinking cats. If I want to make any empirical judgments about the creature in front of me and to prepare myself to make similar ones in the future, I need to make a decision. And that decision is a free choice. You make it for good reasons, that is still a free choice. The decision is the crucial piece here. That's what open texture does. It introduces this sort of diachronic contingency into all the concepts in which it is present. Weissman says that all of our empirical concepts contain pockets of open texture. And on the off chance that we actually encounter it, we need to start making those decisions. And those decisions then become part of the criteria by which our concept is applied in the future. The most famous case of this in recent years, one that may have already sprung to your mind, is the case of Pluto and the dwarf planets. Upon the discovery of many Pluto-like objects, the International Astronomical Union convened to make the decision I just described. Are these weird planets, or are they not planets at all? With the understanding that whatever decision they make would shape future research, and thus was a matter of some importance. I actually have this from the mouth of one of the people who was there, which was pretty exciting, Stephen Dick, who said that the vote actually came down to 2 votes. First, whether Pluto was a dwarf planet. Second, whether dwarf planets were a subset of the class planets or their own thing. As you may recall, the vote went for yes on dwarf planet and their own class. So that's the basic idea, that empirical concepts exhibit this kind of diachronic contingency because our definitions fail to guard against all potential situations in which we might want to use these concepts. We're forced to make these free decisions over time, and when we do, we end up modifying our concept. So Question is, does the concept prime number exhibit open texture? Weissman himself would answer this question with a straightforward no. He doesn't think that mathematical concepts exhibit open texture at all. However, there's a little room for ambiguity here. Prime number seems like it's pretty well locked down, right? You're not constantly in doubt that you might run into a novel kind of prime number next week. But it wasn't always so. Really, the question we should be asking is this: has the concept prime number ever exhibited open texture? There's a growing consensus amongst philosophers of mathematics who read Weissman, of a fairly small set, I won't deny, that Weissman's insistence that mathematical concepts don't exhibit open texture is proved wrong by a text that almost any philosopher of mathematics has already read, Imre Lakatosh's Proofs and Refutations. Proofs and Refutations is nothing else but a reconstruction of a centuries-long process of decisions that led to the closure of the open texture of the concept of polyhedron, which had previously been full of big gaps. Good topic for Q&A if you want to talk about that. But back to our question. Has the concept of prime number ever exhibited open texture? I think the answer is yes. So I'm going to answer it yes in two ways. First, trivially, and second, a little less trivially. So, trivially, this is the first definition of prime number we've got on the books. This is Euclid. For Euclid, a prime number is that which is measured by a unit alone. There's a patch of open texture in this definition. Anyone see it?
The number 1.
It's the number 1.
Is that, yeah.
It,
Is that what you're...
oh, sorry.
You might need to speak up, Siddharth.
Oh, sorry. Yeah, I was just saying, so the number 1 is measured by a unit alone. And at least currently we don't take it to be a prime number.
Indeed. Yeah, that is the primeness of 1 is left crucially open by Euclid's definition. Euclid himself didn't consider 1 to be a prime because Euclid doesn't really consider 1 to be a number at all. He considers it to be the unit, which is a different kind of thing. But the question of the oneness of primes, or the primeness of 1, rather, was not settled by Euclid and was a topic of discussion for many a century thereafter. In fact, you all know the correct answer here, right? That 1 is not prime. Now, this is what everyone learns in mathematics now. But that consensus wasn't settled until roughly the start of the 20th century. Up until then, whether a math textbook would feature 1 as prime or not prime was kind of up to the author. And you can find textbooks that do both. And interestingly, the reason for why we settled on 1 as not prime isn't really a mathematical reason at all. We could operate with a prime 1, but if we did, we'd be forced to reword a bunch of important theorems that we'd like a lot. The fundamental theorem of arithmetic would take take up a lot more space on the page because we have to accept 1 everywhere. And lots of similar little aesthetic tweaks. Basically, the reason we don't consider 1 to be prime is an aesthetic reason. It makes our lives a little bit harder. 1 was in the open texture of prime. We made a choice. It was not logically forced by the nature of primeness. It was something we had to choose. So the concept of prime number has exhibited at least that much open texture. We could have gone the other way. We could have made the other choice. Now, that doesn't really change anything for the argument I'm making. The primeness of 1 doesn't matter when we talk about the factorization of these semi-prime numbers, because factoring it by 1 would simply do nothing. So we need a more substantive argument if we want to make the open texture stick here. Up until this point, I have kept speculation about what other planets might or might not be like to an absolute minimum. The activity of imagining different ways in which an alien civilization could develop is both completely boundless in scope and bounded by the limitations of my human imagination. However, in order to make concrete the possibility of miscommunication based on open texture and the contingency it would give to the concept of prime, I can no longer at least avoid at least a couple of visits to some alien planets.
What?
I will try to limit the fanciful nature of these fables as much as I am able. After all, my goal is to conjure an image of a communication scenario that is, beyond the problems caused by the open texture of mathematical concepts, completely idealized, ideal for interaction. We can imagine the inhabitants of these worlds as arbitrarily, biologically, socially, intellectually similar to ourselves. They can have 2 legs and 2 arms with 5 fingers per hand. They can have science and mathematics that's comparable to our own. They can have radio telescopes that receive in the kinds of frequencies we're transmitting. And they can have access to the concept prime number. The only variable I will change is their history of mathematics, and with it, the development of that concept of prime number for them. So let's consider 2 worlds conveniently located in the direction of the M3 globular cluster, that's this fellow here, to which the Arecibo message was sent. These worlds are just like our own in all respects, save the history of their inhabitants. They look, think, and act like human beings. They have similar concepts, similar institutions, and similar reverence for mathematics as we do. However, they didn't have a Euclid or an Euler or any other specific earthling you happen to name. They have their own history of mathematics, and I will argue that it is at least conceivable that a different history of mathematics alone is enough to defeat the Drake picture strategy. All right, so our first fable takes us to a place I have humorously called Twin Prime Earth. It plays host to a mathematics that is very much like our own. However, the weight that ancient mathematicians of our world placed on geometry, their ancient mathematicians placed on number theory. This advanced understanding of numbers and their relations led them to discover and prove the twin prime conjecture before developing the concept that we call prime number. The proof of the infinity of the twin primes became a celebrated and oft-taught result, known to even the least mathematically curious engineer. Eventually, it would be discovered that there are some non-twin numbers that also share some of the properties of the twin primes. Call them singleton primes. These numbers proved a conceptual challenge for denizens of twin prime Earth. Were they prime numbers with an unusual property, singleness? Or did their lack of the crucial property twinness disqualify them from the moniker prime? Were they an expansion of the concept of prime number or a deviation from it? Eventually, the mathematicians voted. They would remain with their original concept. A few recalcitrant mathematicians continued to study these single primes, but their results garnered little further attention.
So, sorry, Jennifer, I know you might be like, it's difficult for you to understand because you live on Earth and not on twin prime Earth, but help me get my head around how one can state the twin prime conjecture without the concept of prime number as we have it.
Well, so crucially, we can't solve twin prime conjecture ourselves.
But we can, but even stating it.
So the statement would have to look quite different. It would have to say that there are these pairs of numbers that have these unusual properties.
But that property is a conjunction of 2 properties. One is of like multiple properties, right? Like a twin prime has 2 numbers that differ by 2, and each of them are prime. Whereas here you're suggesting there's some way to get at that concept of a twin prime without sort of that kind of conjunctive definition, right?
Yeah, so obviously we can't do that. The idea here is that in this, for one, we don't even know that the twin prime conjecture is true. So the idea is that when they come to this proof that shows where that there are infinitely many of these pairs, And the way they get to that proof, which we do not currently have, will give them a way to talk about these things that for which the concept of primeness comes out as a kind of secondary thing. The
So they have
twinness.
latched onto some other property that somehow has picked it out, picked the sequence out, right? And then they're studying properties of that sequence in some way.
Yeah, the twin. I won't deny that I chose the twin prime theorem here, both for its simplicity to explain and because I wanted to make the twin Earth joke. If there's another proof about subsets of prime numbers that you would consider to be more plausible, that can be subbed in here without loss.
Okay.
So the idea here is that when the twin prime Earthlings take their mathematics classes to get their physics degrees so that they can go play around with radio telescopes, they learn this twin prime theorem and how to prove it. They probably all have a list of twin primes up to 200 memorized, and their alien hearts perhaps even skipped a beat when they noticed that one of the factors in the number of characters in the signal they just received from deep space is the familiar prime number 73. But 23 is not a twin prime. It is unremarkable to them if they do not consider if their notion of prime number is smaller than ours. This kind of example would be familiar to a reader of Proofs and Refutations. It's sort of what the student Beta is arguing for when he proposes that only Eulerian polyhedra be considered polyhedra at all, to turn the that which is to be proved into the definition. When mathematics discovers a putative property of a concept under consideration that applies to some of the examples of the concept, but not all, mathematicians always have a choice here. Either they can reject that property or alter the extension of the concept to fit it. Eventually, things like that seem like the results of a proof become definitive of the concept itself. Perhaps we would be justified in calling the mathematicians of twin prime Earth to be too conceptually conservative. I don't think we can really call this impossible. Our next table. In the inhabitants of the world of pure imagination, like their mathematics abstract. This love of the intangible led them to develop a very general concept of number quite early in their history. Natural numbers quickly gave way to integers, complex numbers, and even quaternions, well outpacing the development of other branches of mathematics. When this species developed a notion of prime number, it was a more general notion than most non-mathematician Earthlings would imagine. Our familiar prime number concept in the natural numbers remains, but is joined by many others. All the multifarious varieties of primeness that go on Earth by different names. In the world of pure imagination, they are simply prime numbers. The entire extension of our concept of prime number is contained within theirs, but theirs is many times broader than ours. When human mathematicians developed notions of primeness suitable for use in the complex plane, we gave these primes new names. We were faced with the decision to either call these new numbers something other than prime, or to call them primes with a new property. We chose the former. The denizens of the world of pure imagination chose the latter. And the idea is that after all these additions, this incredibly broad notion of prime just doesn't have the kind of incisiveness that ours does. When you have such a broad concept, noticing patterns of primeness is commonplace and not remarkable. We may fear that radio telescope operators in this world would react to the natural prime factors of our signal as a mere triviality, no more notable than seeing the word cart horse and remembering that it is an anagram of orchestra. Sure, they might recognize that 23 and 73 were prime numbers of 1,679, but they may also recognize other prime factors when they construe the number in different ways. 1,679 only has two unique prime factors using our concept of prime after all. A broader notion would render the uniqueness of prime factors much less likely. In this way, again, our message could fall on eyes that could never recognize it. by reason of the history of mathematics alone. We might be justified in calling the denizens of this world too conceptually liberal. They're missing something by having such a broad concept, but I don't think we could call them impossible. So these fables are necessarily very, very limited. Of course they are. They're limited by my all too human imagination and the categories that human mathematics in which I have been schooled was framed. Open texture typically lurks in the unconceived, but our ability to find it doesn't. One of Weissman's points is that though it's often easy to prove that a concept does exhibit open texture, it is almost impossible to prove it doesn't. Weissman indeed thinks that only concepts in extremely formalized domains are totally free of it, such as the rendering of a game of chess in standard chess notation. But even then, all we can say is that we suspect there's nothing wrong in our conceptual capture, not that there isn't. And so here's my argument. If it is the case that our concept of prime number has exhibited open texture before, as I think I've shown it has, it could have developed differently, simply because we've made different decisions. If that's the case, then a different species that made different decisions could wind up with a different prime number concept, even if they started from the same place. And an arbitrarily similar species to our own, thus, could have a concept of prime number that cannot pick out the prime numbers necessary to read the Arecibo message, simply because their history of mathematics is different. So, a couple concluding thoughts. It may seem like this conclusion is, in some ways, not a very big conclusion at all. After all, I've just at best made slightly more unlikely something that was already extremely unlikely in the first place. Alien contact is no guarantee. We can try to build the best strategies we can, but we cannot really reasonably expect that any of them will be a surefire thing. There's just too much we don't know. However, I would like you to consider that what we have done here is taken a question out of the Platonic heavens and placed them within our own. If it is the case that many, many species recognize our messages, notice the semi-prime structure, and send us messages back tomorrow saying, hey, nice message, love the primes, then I'd be prepared to say that my argument was probably not that good. That this philosophy of mathematics question, whether or not the notion of prime number exhibits open texture, has become an empirical question. Waiting for aliens to respond is not a great method of settling a philosophical dispute, but it would settle this one, and it's empirical. In that eventuality, though, where the aliens sent us a message tomorrow letting us know that they heard us loud and clear, I think I'd be happy enough to be wrong. All right, thank you very much.
10 minutes for questions, so Ramesh, Peter.
Thank you. That was an interesting angle on this communication question. And I certainly buy your argument that, we may think it's obvious that these primes are the way to interpret the sequence of whatever these blips are, and it may not be obvious to the other party. That part is fine, and so maybe you don't get the reply tomorrow. But if there is a civilization that has come up to the point of being able to receive and interpret radio signals, I'm going to assume that they are of a scientific nature and they are problem-solving kind of creatures, that they will have mathematicians who don't play by the rules. And, I think it won't take very long before somebody will come up with the idea of, maybe these characters use this concept or whatever. And, the fact that when you get the right interpretation, there is a pattern they have a way of proving to themselves whether a particular interpretation is good or bad. So my guess is that it'll take a while, but they will get it, especially if you send multiple messages and there's only one way of reconstructing them so that they all look like they have information. So I would say more optimistic than the message you sent.
Yeah, no, I won't deny that I also think that's probably true. But I also want to say that that's optimistic in another sense as well, because the parallel argument, or I guess the reverse argument, is that we also hope that when we receive a message, if we receive a message, that we will be able to make that same kind of move, that we won't mistake it for noise. And we think that for good reasons, and I certainly wish to believe that that's the case. But the idea with the prime numbers is that it's supposed to be completely obvious. And I think it's not necessarily as completely obvious as it seems.
Peter.
So I was wondering, we study bees, definitely a different species, no mammalian common ancestor. I have to go back 600 million years. And but we learned how to decode the waggle dance. And we know that they communicate distance, quality of source, and direction. So suppose we got a message from far away in the universe, and they said, identified all the near black holes, because that's where they get their energy, and they give a distance, they give a direction, and they give a quality, how useful they would be for extracting energy. We would definitely, I think we would definitely consider that we've shared, we've learned there's been communication, even if we have no idea what the underlying whether we have concepts that pick out not concept and concept in a verificational sense of the kind that, but we can go look, we can say, okay, we see it's coming from Alpha Centauri and the 5 nearest black holes are these, and these. The directions match, the quality of Penrose accessibility for extracting energy looks really good. We don't know what they're like. We don't have a form of life that we can identify, but we would nonetheless figure that something's been communicated that's pretty useful, sophisticated. Something's gone on here.
Yeah, so one point that gets brought up. One point that often gets brought up by people who are responding to this Wittgensteinian argument about the lion is that Wittgenstein should have asked some lion tamers. It's simply not the case that we've failed to understand lions on any sort of systematic basis. The idea is, and I think a better reading of Wittgenstein is actually perfectly okay with this. The point here is not that we don't share concepts. It's that when we are in a position to actually get to know another, to observe the connection between what they do and the noises that they make, it's actually not that hard for us to come to have a kind of association, assuming that the connection between their behavior and utterances is predictable enough. That is, it's not random. The trouble with the radio situation is that it severs the link between communication and behavior. So if the aliens were indeed able to communicate to us the locations of these black holes, we would have a very good reason to think that we are dealing with an entity that we can talk to, that understands us and that we've correctly understood. The trouble is that to communicate that information requires some sort of way to translate whatever sort of signal they send us into that information, which is quite easy to do when you're able to spend a lot of time with the other, looking at the correlation between what they do and what they say. But on a single communication straight shot, maybe not. The trouble is basically that we are our communications with very distant entities are almost necessarily one-offs. It takes so long for message.
Isn't that a kind of supplemental assumption? I mean, it seems to me we could imagine getting a 10-year transmission from these critters about where black holes are, about where, the analogy of how bees communicate flowers, distance to flowers, quality of the nectar, all the kinds of things that the waggle dance does. And we can have quite a lot of information in 10 years of continuous transmission, or maybe it's a video transmission looking at, things through their telescope. I mean, it seems to me a supplemental and just an added, you're making the argument for knowing more complicated by assuming that it's one-off or it's just a little bit of information. What if it's a lot of information? What if it's 1,000 petabytes, like libraries, all the libraries that have ever been made amount of information. There's no reason we can't get that from radio. Well, it's not easy, but.
Well, the point is that how would we know that this is information at all? The point at which we start interpreting it, we start coming to see this as a thing that could even hypothetically communicate the location of black holes, requires us to have already done the equivalent of factoring the prime number. That's sort of what's at issue. And the problem is that without sufficient back and forth, we can't communicate that step independently of the information we're trying to send. Like when someone sends you a video file, your computer needs to have the right kind of video codec in order to turn it into something you can see. Really what I'm arguing against here is the plot of the film Galaxy Quest. It's simply not the case that a television signal from an Earth television broadcasted to space, even if it remains coherent, which it wouldn't, would be something that an alien television receiver would be able to interpret into an image.
Ellen, do you want to ask your question?
Oh, yes. Hi, Jennifer. Thanks for the talk. Okay, so I really liked this way of bringing down the question from the sky as a way of speaking to kind of an empirical topic. And I think, Drake's equation does a similar kind of move, for me at least. And I also think it kind of makes sense to think about the openness of texture of concepts as a matter of degree, not of kind. And so like some mathematical concepts might be more open if there's more dispute about them and so on. So what this made me wonder is the flip side of the argument. So what might be some concept, some mathematical concept that in this context has less open texture or is even more closed than the concept of prime? And so like the lead to this is like, do you think that the concept of prime is simply the best we can do in terms of concepts that are sufficiently closed enough to try to use?
It's a good question. It's certainly the case that I can't say that the prime numbers were a bad choice. And that I can think of many worse. So somebody who is inclined towards a kind of Kantian picture of mathematics might say that counting itself is more basic and universal, that it is less open, arguably the very basics of plane geometry. But even that is actually, there's contingency lurking everywhere. I'm of the opinion that there's probably no concept that we could really call permanently closed. That is, there are concepts we can call closed now. People have argued that the concept of prime number is now closed for us. We've successfully nailed it down and rooted out all the unexpected bits. There are people argue about this. But at least that's what Weissman thought. But we can't really, I think, say this of any concept that we had to develop. And we had to develop basically all of our interesting concepts. So I'm not sure that there's a better option. If we could figure out a way to do it with plane geometry alone, that'd be pretty interesting, but I cannot think of such a manner.
So we're running close to time, but Delilah, do you want to quickly ask?
I think my question just piggybacks off of what Helen was asking. If there some of the concepts we can at least try to identify where we made decisions along the way, doesn't it make it that some are better options than others, at least in attempts? So you were talking about this Arecibo message that was divisible, but maybe they wouldn't consider single primes very important. So maybe we should just pick messages that line up nicely when you're using twin primes. Like there are some things that are less vague than others, like whether you have the idea of single primes or twin primes, this is something you would come to. And are there not some questions that have to have been closed to some degree for them to have this kind of communication anyway? If we're taking a prior of they can receive radio signals, can we not identify the mathematics needed to that and study where we've made decisions and try to pick the things that should be less likely to be open, to Helen's question of degrees of openness?
To some extent, we do that by our choice to use radio waves at all and the choice to use the frequencies that are used. It's deliberately done in such a way that these frequencies are not easily conflatable with any natural phenomenon. One of the ways people often talk about being certain that a signal received is an alien signal on the passive SETI side and the receiving of the messages would be that if it was a signal that just sort of beeped out the prime numbers and nothing else. That's not a very informative signal, but it's the sort of thing that people suggest as a possibility. That has the same problem, of course, but yeah, so I think the ability to look into the past of these concepts and look at the places where decisions were made should actually help guide us towards better methods, under the understanding that we can't ever quite get there. There's always going to be a limit to how certain we can ever be, which is a predicament familiar to anyone dealing with SETI at all. Certainty is never really on the table. But yes, I do think that investigating the places where decisions were made in our concepts can help us find contingency that might no longer be obvious to us, but might be obvious to them.
Okay, I think we should end. Thank you. Let's thank Jennifer again. And yeah, if you have other questions, I'm sure you can email Jennifer.
Yeah, please do. Thank you for having me. Thank you for listening.